All right. So as you have realized that many people had kind of a lot of queries on calibration and the observation, the way we have done it. We have Nirupam, who will be Professor Nirupam Roy from ISC. So we will be actually looking deep into it, and he will basically take over this session to kind of rigorously work out the calibration and flagging and calibration part. So
yeah. So basically, there is a short change of our small change of our plan, and because we received many questions, we think we will, instead of hands-on session now, you can continue with your hands-on session, but because there were many questions, we thought we'll take a jump forward and basically describe few more things about the data, how the analysis is done, and so on, so that you will probably be able to connect more with the things that you are doing. So the starting point is what Naren have derived, sort of the very rigorous derivation. And if I tend to write in smaller font, just warn me so that I make it bigger so that it's visible from the back. So what do we do in radio interferometry is that we have a quantity which is called the visibility, right? This is what we are measuring. These are the correlations that are being measured when I am using an array of telescope as a single telescope. By the way, just for the sake of completeness, an array can be used in different modes, okay? The same telescope, say GMRT, it can be used in a few different modes depending on how you are combining the signal, okay? So people who are, for example, not interested so much in getting the detailed structure of the intensity distribution in sky may choose to use it to add the data together in a slightly different way to maximize sensitivity to certain other type of observation, right? Pulsar observation, for example, is very, very different from the way the regular interferometric imaging observation, imaging or spectroscopic observation is done. There are ways of combining things in an incoherent or coherent array, but this, we are not going into that aspect here, but keep that in mind that the same array, depending on how you are combining the signal that's coming from each of the antennas, can be used to do various things, okay? And the one that we are focusing is when we are using is in the standard interferometric mode, where what you are measuring, the quantity is visibility, right? Which is related to the sky brightness distribution, right? It's related to the sky brightness distribution. This quantity I here is the intensity or specific intensity depending on whether I'm measuring this over a narrow range of frequency or not. And how it is related? It's related through this approximate Fourier transform relation, right? This is what we have seen. So this is minus 2 pi I UL plus VM plus NW DLDM and then you integrate it over the L and M, okay? So this is the Van Sitter-Zernike theorem, and you can reduce it to more useful form in two specific conditions, okay? One specific condition is, so remember here now, so what are these quantities? V is the visibility which comes from your measured electric field in different antennas, right? These antennas are separated by some distance, which are often called baselines, okay? And these quantities, U, V, W, these are the baseline vector components, okay? So I have two antennas and I'm just looking at the separation, not the actual value of their position, but the separation only, okay? Which means that if I have a real plane X, Y, Z or something, I have one antenna here and one antenna here, okay? This is, let us say this is my XY plane. Then in the UV plane, when I'm measuring this, okay, I have a separation in delta X, which is a very small value. So let's say if I define this to be corresponding to my U coordinate, I have a small value here. and then a large value separation is y. So I get one data point here, which corresponds to separation between these two antennas, right? So this is what I will be calling U and V, right? Of course, the same antenna, you can say this is the separation vector or that is the separation vector. Then you can also have a minus U minus V, which will be a point which is here. So if I'm measuring the correlation using these two antennas, what I'm measuring is V UV for this point or V minus U minus V for this point, okay? Now this is one interesting thing about the Fourier transform. Sky signal is real, which makes ensure that V UV and V minus U minus V is same. So you measure one quantity from two antennas, you get two data points on your Fourier sampling, but they are identical, they are the same value, okay? Now if I add another antenna here, then I get another baseline and another baseline, right? So then I get few more points. Okay, so if I have some n number of antennas in an array, the number of baselines that I will have is NC2, okay? But of course, because VUV is same as V minus U minus V, I am also sampling the other part, okay? Now, what am I sampling here? As I said, that under two assumptions, these get reduced to a bit more useful case. One case is where, so what are these quantities? UVW are the separation vector, right? And they have a Fourier conjugate relation with LMN here. Okay, this is not yet an exact Fourier transform, but somewhat like a Fourier conjugate relation with L, M, and N. This L, M, and N are the direction cosines that I am carrying out the observation for a particular direction in the sky to put a coordinate system for that. Of course, because for an observer, everything is on an imaginary two-dimensional surface of a sphere, I only need two of the direction cosines. And in fact, you all know that out of the three direction cosines, only two are independent because I have also the condition that they add up to 1, right? So these are about the direction cosines. And then you are integrating over all that direction for the source, right? To get what will be your measured visibility. This is what my interferometer can give. I am interested in this. I want to know how the sky look like, the two-dimensional intensity distribution on the sky. What I can measure is this, but I cannot measure this as a function. I don't know the value of this VUVW for any given point of UVW. I only know it for a few discrete points for which I have the separation vector available, right? Now, one can first think about it that let us say somehow my W is 0, okay? So there can be various cases where you can set W to 0. What is W? W is so I have drawn here U and V, of course. So the third component of my separation vector is W, okay? Where does this W come from? Let's say I have two antennas here and I'm looking towards a source which is just up. Then the separation is always what the source is seeing, right? From like if you put yourself in the position of source and look at the two antennas, what separation you see, that's the separation vector. And in this case, it may have some X and Y component, but there is no component which is along the direction of my observation, okay, along the line of sight. So in that case, my W is 0, okay. However, if I'm looking at another direction, I have the two antennas here on this plane, and I have a source in this direction. Along the direction also, along the line of sight, there is a component, right? So that is the component which is the W component for my baseline vector. If I have two antennas and they are looking towards a source here, okay, then their separation on the plane is this much, right, in the real space. But that can be decomposed into two components, one which is along the line of sight and one which is perpendicular to the line of sight. These components give you U and V. The east-west and north-south component of this separation the projected separation that the source will be seeing for the two antennas, the projected separation, the north-south and east-west component of that will give you U and V. Okay? This is what will give you W. Okay? Now, there are two ways of setting W to 0. By the way, I'm not repeating things, right? This has not been discussed earlier in detail. So I think, so there are two ways you can make this W 0. Okay? One is that there are some telescopes, some interferometric arrays where this dish is not here, this dish is here. What happened is that they put all the discs on sort of a mount together, and that entire mount is moving when you are doing the observation. So they are not on the ground. You do not pick up a W component. Okay? There are some cosmologists who use telescopes like this, small telescopes. So the platform is not very big, but multiple elements there, and you want to do interferometry, and the entire platform is sort of moving, so that there is never a component which is along the line of sight. So W is always 0 there. Okay. The other thing that you can do, you can say, I will take this antenna virtually up here. How do you do that? You introduce some extra delay for this path. Okay. You have two antennas, and you say, whatever signal I'm getting from this antenna, before I correlate with the signal from this other antenna, I will add some delay, which is equivalent of how much this wavefront must have taken time to travel and come to this antenna. And you compensate for that exact amount of delay. If you do that, then virtually you can think of your antenna is located here. Okay? That also makes your W 0. Okay? The difference between these two, of course, is that here you can make this correction only for a particular direction. So the direction which you are looking towards, that direction is generally what is also chosen to be where I set this W to be 0. Okay? And that direction, if I'm doing this, if I'm actually compensating for this extra time and virtually taking my antenna up here so that the W becomes 0, that direction is referred to as the phase center. So if you come across this term called phase center in the context of interferometry, phase center is referring to a particular direction in the sky for which I have set the delay for different array elements, different antennas in such a way that as if there is no component of the baseline vector along the line of sight for that particular direction. We will often choose this phase center to be same as our pointing center. What is a pointing center? I have this antenna here, okay? And each antenna, they have certain directionality. Like, forget about interferometry and everything, I have an antenna. It generally will be much more efficient to picking up things in this direction. Okay? So this is sort of a polar plot of how efficient it is in picking up emission from a certain direction. This is what is referred to as the primary beam. Primary beam is a property of a single disk. Okay, a single element, not of your array. It's property of a single element, right? Once you have a primary beam, you know that this direction is where I have the maximum response, right? Which means if I want to observe a source in this direction, I would like to point my primary beam towards that direction to get maximum response. That is my pointing direction. You will also do most often the time delay compensation for the same direction to make that also the phase center, which means the region on the sky that this element is being able to observe, the center of that region is also the region where your W term is being set to 0. Okay? If you go a little bit of details, you will see that the primary beam is actually related to the Fourier transform of the aperture. Whatever aperture you have, okay, if it is just a circular aperture, then it will be a primary beam with sort of a airy pattern, square of that, right? So you will get the main lobe of the primary beam and then the side lobes and so on. Huh? But without going into more details, so this is our phase center. This is what the W, how W is defined. And I can choose to make this value to be 0. If this is set to 0, then this expression will get reduced to ILM and I can absorb this factor here and sort of call this as my I prime. That instead of now Fourier transform of I, I'm getting Fourier transform of a quantity which is called I prime, and then this become an exact Fourier transform. Right? Now this become an exact Fourier transform from I prime if I can somehow set W to 0. Okay, and of course, you know L and M. So you find out the Fourier transform, you have this thing, inverse Fourier transform to find out I prime, then correct it to get ILM. That can be done. The other extreme in which you can also do the same thing is if you restrict your observation to only a small part of the sky. Okay, so that if you are restricting it to a small part of the sky, what happens is that this term here, so this term here will become very close to 1. Okay, square root of 1 minus L square minus M square will become very close to 1. So I can ignore that. And then this is n, right? This is n. So this become 1. So I get a factor which is e to the power minus 2 pi I w that does not depend on L or M. So I can pull that out of the integral. And in that other case, so this equals is not this equals, right? It's coming from here. So in this case, it will become e to the power minus 2 pi I w, and then again an exact Fourier transform. Okay, and in this case, when you are saying that my value of L and M are small enough, okay, in that case also it become an exact Fourier transform. It's often customary to define, instead of I prime here, it's customary to define a V prime, which is sort of your V into e to the power 2 pi I w. Okay, of course, you know the W for different direction, you correct your visibilities by this factor, then this V prime is an exact Fourier transform of your ILM under that assumption. Okay. So the key thing is that I have this relation, which from now onward, I will not worry about these details. I'll just say that my V and I are related by a Fourier transform operation. Okay, but remember this is an approximation. So with this, now we will think about, this is what we have done. I have some n number of elements in my array. So I have NC2, some NC2 possible pairs. On those possible pairs, on those UVW value, I have measured some visibilities. Okay, these visibilities are Fourier transform of my sky intensity distribution. This is what my interest is. So I will take those visibilities, do an Fourier inversion to get ILM. Okay, this is the basic idea. Okay, now there is a very interesting thing about Van Sitter-Zernike theorem, and those who are interested should look at it. It has very beautiful physics encoded there, which is connected to the coherence of electromagnetic radiation. Okay, any interferometry is basically you are playing with the coherence of electromagnetic radiation. Okay, there are two types of coherence that we normally talk about: a temporal coherence and a spatial coherence. If you broadly know two different types of interferometer, Michelson's and Young's double slit. Michelson's is when you are looking at the temporal coherence of an electromagnetic wave, right? You have to ask this question: what is my light source with which I can do Michelson experiment? A very stabilized laser has a very long coherent time scale. So you can move one of the mirror by a huge amount and you can still produce fringe because it has high temporal coherence. Okay. Whereas Young's double slit, you don't worry about temporal coherence at all. What you are worrying about here, Van Sitter-Zernike theorem, is you are worrying about the spatial coherence of your electromagnetic field, right? And spatial coherence of the electromagnetic field, if you look at it, one can, from the point of view of a double slit experiment, right? I can ask this question that suppose I have a source of some size A here, okay, a characteristic size A here, at a distance L from this source, from this screen where I have the two slits. And this separation is something like D. Okay. If this is a point source, okay, if this is a point source, that means that it has, in a way, infinite spatial coherence. Right? The electromagnetic wave coming from there is perfect spherical wavefront. So it does not matter how far away these Ds are. You will be able to pick up coherence. Okay. But if it is not, let's say this is a thermal source. Emission is coming from a lot of atoms which are vibrating but not knowing about each other. So amplitude and phases are random and coming from a size, typical size of A. Okay. Your light bulb, sun, star, okay, whatever it is. Then you can ask this question, can I do interferometry with that? The answer is yes, you can do, but it will depend on what is this value of L and what is this value of D. Okay. For a particular case, a small d may give you a fringe. You keep on increasing the d, you will wash out the fringe. Okay. And the number that the coherence, it depends on. So if I look at an area here, right, the coherence area, I'm taking a bit of deviation of what I promised about calibration, but I think this is interesting. So I'll just talk about this and then move to calibration part. The coherence area for a given source, okay, this scale as so it will depend on the size and it will depend how far away it is and it will depend on my observation wavelength. Okay, so lambda square L square by A square. This is a bit non-intuitive result, by the way. What I'm telling here is I keep on increasing this L, okay, and my coherence area keep on increasing, which means I have some source here and I'm measuring things here, the spatial coherence is less. When you move far away, your spatial coherence increases. Okay? And this spatial coherence area will determine whether you will be able to tell me that this is just a point source, like a completely coherent source of radiation, or it has some structure that it's incoherent. Okay, is this idea clear? If I'm looking at things coming out from a point source, right, and I measure the correlation of electric field with certain separation, okay, I will find them to be exactly correlated because this is a delta function, this is a point source, this is just spherical wave which are coming out from there. So they are always with a fixed amplitude and phase relation, their correlation will be highest. Okay, but if there is an extended thermal source here, you can think of all of them to be point sources, but they are like incoherently emitting. There is no phase relation. Then what happened? This thing gets sort of zigzagged, right? Then you measure it with certain baseline. This is what you are doing when you are doing this, by the way, right? You are doing it here also, but radio astronomy is just this. You now have to find out the coherence area, the coherence length scale on this waveform to find out the structure of the sources. Okay? And because of these dependencies, a source which is either bigger in size or smaller, like nearer to us, bigger in size or nearer to us, will have a much smaller coherence area, the spatial coherence area, right? And this is the reason, just with a few millimeter aperture of your eye, you can find out that the sun is an extended object. Okay, so for sun, if you calculate this for sort of a filtered light, you use some small range of lambda in optical, this number will come out to be some 3 into 10 power minus 3 millimeter square or so. Okay. So to understand this waveform, how they are correlated spatially, right? You need to sample it over a very small area. That's it. You get the structure of sun. For a star, this L is much larger, right? This number will come out to be of the order of 6 meters square. So over 6 meters square area, a starlight, which is again a thermal source, all atoms are like incoherently emitting, But over 6 meter square area, there is coherence. Okay, this propagate further and further away, this started becoming more and more coherent. So to find out the structure of a star, you need to sample this and do the correlation over at least few meters. Before that, you do not realize that it's not a point source. It's effectively like a point source for that baseline. The same thing happened in radio astronomy. I get an array where all my antennas are close to each other. Okay, you will not even know whether you are looking at a point source or an extended galaxy. But you go to longer and longer separation, longer and longer baselines, you start picking up information about the structure on the source. Okay, whatever is the loss of spatial coherence or build up of spatial coherence because of the structure, this is sort of the governing principle. Okay, is this clear? Is there any question from here? No? But if you dig up a little deeper into this idea, you will find that it's like a really very interesting aspect of the coherence of the electromagnetic wave that allow us to do all of these things. Yes.
Manchester journey key is for incoherent source.
Any source is coherent or incoherent depending on at what scale you are looking at it, right? Thermal source, it's completely incoherent because I am looking at everything together. You keep on zooming in, an atom vibrating and radiating, that is a fully coherent emission. It becomes incoherent only when a lot of things are coming to you together, right? A simple point source, if it is really a point source, a real delta function, which is emitting spherical waveform, that remains coherent, right? What type of physical source is that? I'm not answering that question. But what I'm telling is that, but then you zoom in, and you will find that this source is actually a radio galaxy, which is very far away. That's why it looks like a point source to me. So for a certain baselines, it's incoherent. It has a spatial incoherence. Now, if you are referring to the derivation of the Van-Sitter journey curve, where we assume that to be a incoherent source, that is related more to the temporal coherence. Because what we use there is, we said, if I have a source, and I have electric field here and here, okay? What we do is that here, when I'm trying to write this, I write some E1, and then if this is E2, then I am taking a time average here, okay? So do I have a okay, like it will only become ILM if 1 and 2 are the same point, okay? This I'm assuming when I'm deriving this, that's correct. That's what you are referring to. Is that
Correlation using the correlator?
yes? So think about it from the point of view of whether a source is an unresolved source or not. A source which is an unresolved source, when I say it's unresolved source, I'm talking about some baselines where it is unresolved. If I go this baseline, it may become resolved. Here it is unresolved because what? Up to this spatial separation, its electric fields is correlated. There is spatial coherence at that separation. That tells me what can be the size of this source. If I know A, I know lambda, I know L, I know what will be the size of the source, or this is related to the angular size of the source. A by L is actually angular size, right? So angular size of the source and the area of coherence are directly related. Fine? You had a question earlier.
So here you are saying like it is connected through Fourier transformation.
Which one?
Like V and intensity.
This is, so yeah, so this is not an exact Fourier transform if I write down in this particular form, but under either of the two assumptions, that if I have set W to 0, this become an exact Fourier transform, but not of ILM, of a different quantity. But this different quantity is not very different from ILM, and if I know this quantity, I can find out ILM. Or under the assumption that my N is almost 1. So I am looking at a very small patch on the sky. L and M values are small. If that is the case, then also this become an exact Fourier transform, but not for V, some V prime, which is this, but again, this I can compute. So both the cases, it served my purpose. I observe something and I can do a Fourier inversion to get I.
What is the periodicity condition on I and
What is the?
Periodicity condition? Like
Okay, so normally, yeah, so that, that rigor we have not gone through, but you normally do it over a small patch and things goes to 0 on that boundary anyway. Okay, and you will see that from here also, what will be the largest scale of emission that you can pick up will depend on where you are sampling it. So exactly like my longest separation will tell me what is my resolution, the smallest separation will tell me up to what scale I can pick up ILM. Anything which is varying in a fashion smoother than that length scale will not even be picked up by your interferometer. Okay.
So coherence area depends on the diameter of source and how much distance between the source and
yes. Remember, these are again, by the way, thumb rule in the sense when I say A, it's not like a spherical source and so on, but typical length scale of the source and the distance to the source.
So looking to the coherence area, how we choose our baseline or something like that?
Or you can say the other way around, the longest baseline determine up to what area you can measure the coherence. Okay, that determine up to what scale you can resolve, because this A over L is nothing but the source angular size. Okay, fine. So with this then, what is the time? We have the first half an hour is gone. Okay. Do you want to do hands-on data analysis or do I continue? I can continue. Okay. So then, because 3:30 we have to stop for the photo. Huh? These are not being recorded. Okay. So this is what we take from here. Okay. From all this discussion, we say that I have some approximate Fourier transformation relation. Now, let us come back to the reality. If you give me the visibility, okay, you tell me this visibility is some functional form, okay, then I know how to do a Fourier inversion and get I. But in reality, what do I have? There is, of course, complications which are related to only the sparse measurement. We are measuring VUV only at a few points. That is the thing we'll take up later. But even before that, you do not measure the Fourier transform of sky brightness. You do not measure the visibility directly. What you measure is you have the antennas, electric field, due to the electric field from the source, you have produced some signal on the individual antennas. That signal has been brought to your correlator using some sort of electronic chain, and you are correlating those signals which have been brought to your correlator. Okay, and there is a lot of things in between which are actually changing what you are measuring. It's not electric field that you measure. It's not the electric field correlation that you measure. You measure something which are all being modified by your instrument. Okay, which means that in reality, the data set that you have been given, we'll now call that as observed visibility. Okay, to distinguish it from what we call the true visibility. Okay, so true visibility and observed visibility are different. They have been modified because of your instrument. Okay, what does the instrument do to visibility? So thing to keep in mind is that visibilities are complex numbers. Okay, complex numbers, things which are being pushed through electronic system which has complex gains. Okay, so what you get here is basically some complex gain modifying your true visibilities. Now this is a loose notation, by the way. Okay, there are a lot of things which I am not writing, because this, when I write this, there is a dependence of U, V, W, then frequency, then time, and all those things. Okay, but it is being modified by, so this is just to illustrate that true visibility is being modified by some gains of your instrument. And these gains are complex gains. Okay, electronic system can change amplitude as well as introduce phase. So complex gains. And then it's also introducing some noise, right? And then in addition to that, of course, this is on the sky and this is on the ground, and in between there is atmosphere, ionosphere, which particularly will affect your radio observations, but also atmosphere in general, including, for example, troposphere, if you go to a slightly higher frequency. Okay, there are various effects which will also be introduced by the atmosphere, ionosphere and troposphere. So ionosphere and atmosphere, right? And it is again, it turned out that it's possible to deal with all of that without worrying too much about separating what is coming from my instrument and what is coming from the atmosphere and ionosphere. Without worrying too much about it, you can absorb all of that in this gain term. Okay, you say whatever change has happened, I will call it gain. It includes your instrumental gains as well as the distortion which the atmosphere and ionosphere has done to your signal. Okay, there will be phase changes due to ionosphere, the additional path length because of the electrons which are there, right? You will have dispersive changes, you will have rotation of your electric field, you will have an overall absorption which is happening in the troposphere, particularly at the higher frequency because of presence of water and oxygen molecule in the atmosphere, which cause an overall decrease of your amplitude of the signal. All of this you can absorb, saying that I don't worry about which part, like I'm not studying atmosphere and I'm not studying my instrument. So I club all of this together and call this simply as gain. Okay. But if you want to study ionosphere and atmosphere, you have to separate out which part is coming from ionosphere, which part is coming from instrument. But for the astronomy, if I'm interested in this, then I don't worry about that part. Okay. But now let us add this complication then. If I have this, this is of course a function of the baselines. Okay. So I will write that as denote here by an index ij. Okay. So two antennas, and if I index them by ij, that is what I have measured. Okay. But then I am also measuring it over a period of time. I'm doing my observation for 3 hours or 8 hours or whatever, right? So of course, that is a time-dependent quantity that I'm measuring. Okay. And then I'm also measuring things across frequency. So this is also a frequency-dependent quantity. Okay, at different frequencies. Now, why we need to do a time and frequency-dependent quantity measurement? That has to do with the same discussion that we are having, that if you, why cannot I just measure, you know, my visibility at ij is related to Fourier transform of ILM. This thing is not varying in time. Why I'm measuring V as a function of time here? This may have a frequency dependence. Whatever source property, it may have a frequency dependence. So I can argue that there has to be some frequency here. But if you again look at the details, you will see that what I can do here, at what time interval and frequency interval I have to do the measurement, has to do with, again, the coherence of my signal. If I average a lot of time and lot of frequency chunked together, then I will actually not having the correlation. The correlation will get washed out. Okay. So the way it works in the system here is that from each of these antennas, okay, let us say you are basically picking up the electric field. Okay, this is not the true electric field, it's being modified by gain and all these things, keeping that in mind, but you are picking up electric field. Okay, and what you sense is electric field as a function of time. Okay, so your antenna is responding to a time varying electric field. Okay, now most of the telescope, the way they will operate is this. They will sample this electric field with a very, very high time resolution. Okay. you sample the electric field or whatever is the equivalent, the signal, right? Electric field times some gain plus noise, whatever, that you sample first with a very, very high time resolution. Okay. That high time resolution, let us just denote by these data points that are like being sampled now. Okay, so you sample it with a very high time resolution. Okay. Then because you are operating this thing at the radio frequency, what you can do is that you can take a chunk from here, okay, and do a Fourier transform. To take it from, so this is a function of time, okay. So in radio astronomy, you get Fourier transform everywhere. In all possible way, you use Fourier transform. What this will give you is sort of a measurement in frequency, okay. Right? So you get this measurement in frequency. You do it for a chunk of data, then you do the same thing over the next chunk of data. Then you do the same thing over the next chunk of data. Why I am doing this? Because you can again show that whatever we were talking about here is sort of applicable truly for a monochromatic wave. Okay? If I take this ET, which has signal from all different frequency and correlate with, let's say this is E1T, and correlate with my E2T from this another antenna, you will wash out the signal. You will not get a correlated signal. Okay? So you try to make it as monochromatic as possible by already dividing the data into narrow frequency channels. Okay? And you can actually do this because you are operating at radio frequency. So samplers which can work at few gigahertz or something can actually do this thing, right? You can sample it at a very high rate, do the frequency, time to frequency Fourier transform, so that now what you have is this give you a few channels, okay, frequency channels, okay. Then you get the next data set in the same way and the next data set in the same way, right? So you are getting the signal as a function of frequency, but also like if I now call the center of this thing as some time t1 and then this part as some time t2, then what I'm getting here is at time t1, right? And then whatever I'll getting from here will be at time t2 and so on. So you get this as a function of frequency and time. Then you do the correlation, okay? But when you are doing the correlation, you do the correlation of the corresponding frequency channels only, right? So that your output here is not just a function of the baseline, but time and frequency both, okay? So while I'm doing this, I have also made this thing complicated because gain is also a time and frequency dependent thing. Okay. And of course, my true visibility is hopefully only frequency dependent and not a time dependent thing. Right? So probably this is only a frequency dependent thing. And then of course I have the noise coming here. Okay. For the timing, let us ignore the noise thing. So I have an equation like this. So now we are in a big problem because I want to observe this galaxy, use all these arguments to find out what is the size of this galaxy or its structures. Then we have built this telescope, we have done all this measurement, we have got visibility, but this is not true visibility, this is observed visibility. And my ILM is Fourier transform of the true visibility, right? So how do I take care of this? This is the process of calibration, okay? The part that I am not talking about is before you do even that, you have to first identify which data is good and acceptable, which data is bad, not coming from sky, but coming probably from some terrestrial sources or some satellite and all those things. Radio frequency interference, identify them, remove all the bad data when your antenna was not working, so on and so forth. And then you end up with some cleaned set of visibilities, but observed visibilities, which are modified by the gains that you need to take care of to get the true visibility. So this is the process of calibration of how do you get true visibility when you have done the observed visibility by doing the gain computation. Okay, and the only way you can do it is if you have some way of knowing this thing for another source. Okay, then you can say for some sources I know this thing, I will observe this and use both of these to estimate what my gains are. Those are your calibrators. Okay, so what are my calibrators? Calibrators are basically where generic thing is where your true visibilities are known. If I know the true visibilities, that is what I will call a calibrator. Okay, and that is what determines how you do the observation. Okay, you observe a calibrator for some time, then you observe your target source for which the true visibility is not known. You use the observation for the calibrator source. There you know the true visibility. You have gathered the visibility using your telescope. So you find out what the value of gain is. Okay, and then apply that gain to your actual target data. Okay, so that's why your target observation has to be accompanied by observation of your calibrator source also. Okay, now what I am assuming here is I observe now some calibrator, and then after some time I observe the target source, and I am assuming that the gain can be applied from here to here, right? But I am writing this gain to be a function of time, so I cannot really do that. Okay, so what do? Is you interpolate. You say I will observe now for 5 minutes, then for 30 minutes I will observe my target source, then again for 5 minutes I will observe my calibrator. I will compute the gains in these 5 minutes and interpolate it smoothly in the time in between, assuming that my gains are varying smoothly in time so that my interpolation is justified. Okay. It turned out we can do better than that, and we can do better than that because most of this gain, the process in which you have measured the visibility, is basically measuring electric field at 2 different antennas and then correlating, combining them, right? It turned out that you can do better than that because if I do it this way, of course, I have a Gij here, right? For each baseline, I need to fix the gain. And how many Ij I have? I have NC2. So I need to solve for the gain for each of the baselines. That's a very complicated job, right? It turned out that for most of the purposes, you can actually write this equation in the form of the gain, which can be decomposed into antenna-based quantities. Okay. Now, strictly speaking, this is an assumption. You are saying that all my gain can be antenna-based. Okay. But it works. Most of the time it works. So you said this Vij is my Gi and Gj complex conjugate times my true visibility. Okay. If I can do that, then it becomes easier. Okay. GMRT, I have 30 antennas. Okay, so how many baselines I have? Baseline is 435, right? NC2, 435. Okay. So if I observe a calibrator source for which I know what is the true visibilities, I can write down such equation for all my 435 baselines. Baseline 1, 2, 1, 3, 1, 4. I know what is the observed visibility now. Okay, I know what is the true visibility for my calibrator. How do you know that true visibility? I am coming to that. But I can write this, that V12 is G1, G2 star, VT12. Right? And I can write 435 such equation. And I can solve those 435 equation for my 30 unknown, which are the Gi, the gains. Okay. So if I have 435 equation, 30 unknowns, this is of course an overdetermined problem. But in reality, it is not, because here also I have the noise. Okay. So once you have the noise for each of those baselines, what you are doing here is sort of an optimization problem. You have some measurements and you have some parameters that you want to determine. So you do a least square, chi-square, some optimization, right? What quantity you need to optimize and so on. People have developed that heuristic over a long period of time. For most of the interferometric arrays, you will find that something called L1 norm, which has to be minimized instead of the L2 norm when you are trying to find out the best estimate of the gains in presence of the noise. Why L1 works instead of L2 better and so on. That has to do with your electronics, your system and so on. But effectively, you can solve this set of equation to get the gains. Okay. Now, here is the next level of complication. When I'm talking about you can find out the gain, and I should have really written capital G here. Okay. So this is a set of assumptions which has gone into it. I'm saying that my gain can be decomposed into antenna-based gains. This is a fairly good assumption because most of the things, for most of the time, the signal is actually in a channel, in an electronic strain, which is sort of separate for each of the antennas. Until the point when you bring them together at the correlator and do the correlation and write the visibilities, they are like in a completely different data path, right? So maybe it's not a very bad assumption, but sometime it breaks down and you need to look, see how you can fix that. But this is one assumption. The next set of assumption which goes into it is that you say, look, my G is a function of time and frequency. And here I take a big jump of faith and say that this G for any of these antennas, right? Okay, I need to find out G as a function of T and nu. Okay. Now the example I gave you, I say I will observe it for 5 minutes, then 30 minutes of my target, again 5 minutes, then I will interpolate. That I was talking about this time variation part of the G, but it's also frequency dependent. Okay. And this is what we take another bold leap, which is basically when I say that this can possibly be divided into two components, one which depends only on time. And let me remind you again, all these are complex numbers. So they have their amplitude and phase. Okay. So you say I can divide it into two parts. One of that is time dependent. Another is frequency dependent. Okay. And generally, when people refer to gain calibration, they are referring to only this part. This term is called the band shape of your instrument or band pass of your instrument. And that calibration is called a band pass calibration. Okay. Now, this assumption is certainly wrong. Okay. This is a simplifying assumption, but this is certainly wrong. So you can do a slightly better job than this by going one more round and say, look, I will use some method to calibrate the time dependent gains. Okay, the actual whatever is referred to as the gain calibration. Then I will do a frequency dependence gain part calibration, my band pass calibration. Okay, but I am not blindly assuming that the band pass calibration has to remain completely time independent. So I will put a weak time variation here. And how I will solve for it? In the same manner. I will observe a band pass calibrator now. After 3 or 4 hours, I will again observe a band pass calibrator. 3-4 hours later, I will again observe a band pass calibrator to calibrate the frequency dependent part of the gain. And then I will do a smooth interpolation of B nu from T1 to T2 to T3 and apply that as my B nu T. Okay. So this is sort of a slightly better way than assuming that they are completely separable. It depends on the stability of your system. There are some telescopes where B nu is actually stable in the sense that I have even done data analysis where I forget to include a bandpass calibrator. So I picked up 1 week before data where the same setup bandpass calibration was observed, and I was able to apply that bandpass calibration. It depends on the stability of your system and how this bandpass is being generated and so on. Okay, it depends a lot on how the signal is being processed in that data signal chain that I was talking about. But this is a generic prescription that you can assume this to be a time and frequency dependent thing, which can be divided into a time dependent part and a frequency dependent part, which is also weakly changing with time, right? And this part, normally either one of this part will also need to take care of your overall amplitude scaling, okay? So you can think of as if you have sort of an amplitude here and then a phase here for this gain, you can, if you want, you can sort of also normalize this so that this will not have separately the overall amplitude can be fixed to 1 here if you want, or if you want the amplitude to be absorbed here, this overall amplitude can be fixed to 1 here, okay? So with this in mind, then what should be our overall strategy for the calibration? So we need to calibrate 3 things. One is my overall gain amplitude. Okay, I'm seeing some source, how bright that source actually is. And that thing is generally referred to as the flux calibration. This, as Naren was also mentioning earlier, you don't need to observe this source again and again. At the beginning or at the end of your observation, or maybe at most twice, you observe a source for 5 to 10 minutes, for which the flux density is very well known. Okay, it has to be very well. Yeah. So you have to observe this source for which the flux density is very well known. And as you know, for most of the sources, this is not possible. There are a lot of variability of sources on the sky and so on. There are few selected sources that people are observing for decades. There are some 4 or 5 sources which people are observing for decades and modeled how their flux vary across time and frequency in a secular manner, the slow evolution of flux across time and frequency. Those are what people use as standard flux calibrator. You need to observe only once or twice during the course of your observation. Then to get the phases, right, for here, what you will be doing is the next step, as I mentioned, you will be observing a calibrator and target source alternately and use this equation to solve for the gain, right? This phase will not only include the instrumental phase, but also ionospheric phases if there is any contribution, and then interpolate here in between. And again, as Naren earlier mentioned, the requirement for this calibration, which is generally referred to as the phase calibrator, that this source should be close to your target field so that you are also getting a good estimation of the ionospheric phases from there. And then you also need to observe something called a bandpass calibrator. Thankfully, often bandpass calibrator can be same as my flux calibrator. This is something where the frequency dependence of the source has to be very well characterized so that I know what is the way that the true visibilities are varying across frequency and use that information to calibrate the frequency varying part of my instrumental gain. This again, you can do once or twice during the course of your observation, and then you can do an interpolation. Okay. So this is the basic idea about the calibration. The data that you have been given, you can now do the flagging and the calibration, and hopefully when you will be following the procedure explained in the write-up, you will be able to connect it somewhat to this discussion. Okay. Any question?
Can we use this phase calibrator as my bandpass calibrator?
You can sometimes use the phase calibrator and as your bandpass calibrator. The requirements may be slightly different. You need to have, first of all, you need to have a good idea about the frequency variation. Okay. Phase calibrators are generally somewhat weaker sources and we may not be monitoring them. So we do not know possibly how the how they are expected to vary across frequency. If I do not know that, then I cannot. But if the source is known, where the frequency variation is known, and how much time you have to use for the calibrator observation depends on how bright those sources are. Because remember, this is some sort of an optimization problem, which means better signal to noise will give me better estimation of the gains, right? And hence, stronger source is better. So flux calibrator, bandpass calibrator, stronger, well-characterized flux and frequency variation is what is required. Phase calibrator, you don't need it to be so strong. You are not worried about overall amplitude, but you need it to be closer to your target field. Okay. Often it may happen, suppose you are observing a source which is close to one of the flux calibrator. You can use that source as your flux, phase, bandpass, everything. Or you happen to come across a phase calibrator which is strong enough and its frequency is well characterized, you can use it for bandpass calibration. Okay, I think maybe last question before we...
For GMRT, you said you have to solve some 435 equations using the noise, but you solve it using noise terms.
No. What I said is that for GMRT, because you have 435 baselines at any given time, right? Any given time when I have this observed visibility, and if I know the true visibility, I can write this equation for all 435 baselines. Okay. And then, but there is also this additional noise term here. So this equation, even if it looks like that there are only 30 unknown, for that time, what is the antenna gain? That's the unknown. For 30 antenna, the number is like 30 unknowns. But the number of equation I have like this, if I ignore the noise term, is actually 435. Right? So it may look like an over constant problem. But what I said, it's actually not, because in each baseline measurement, you also have noise which are independent. Yeah. And I don't know a priori what these are, right? So when I'm trying to solve for gains, I cannot just simply invert this equation because I don't know the noise. So this becomes an optimization problem in that case. It's not an over constant problem.
Okay.
Okay, fine. So we stop here. Of course. Yeah, and of course I'm around, so feel free to catch up. And tomorrow we will anyway continue with this discussion and more hands-on and everything. There is. Okay, so is there any announcement? I think there is a.
Let us have the group photo once more, because some of the teachers were missing in the previous one right now, and then we have the tea and should get back at 4.
Yeah, and
there is one more lecture today.
Yeah, one more request is that you have the PDF file where instructions are written very clearly. So I would suggest that you guys go and take a look, find some time, and try to play around with this, with the instruction. So tomorrow we will have a little bit, advantage on that. Okay.
Yeah. Keep your dinner, work, come back with the